In this video, I'm going to try to explain and discuss and try to use some of the volume formulas for some of the popular solids that we're going to see. The good news is that you don't actually have to remember these formulas ever, because whenever you're taking a test or quiz, in my class, or if it's the Park or the SAT, you're always going to have a formula sheet that provides these things to you, which is really nice. But still, it's worth talking about because it grants us some insight on how and when we could actually use these things. So, for example, if I want to talk about the volume of a prism, which is this guy in the top right, a prism is more or less defined as being a solid with two bases that are both polygons, and they're going to be opposite and parallel to each other. So in this case, because the bases are rectangles, this is a rectangular prism. Suppose we start with just a rectangle, like the yellow base of a rectangle. Imagine a sheet of paper, which is almost a rectangle. It's actually a rectangular prism because it does have depth. It's just that paper's so thin we don't really see that third dimension of height to it. But imagine I have a plane, more or less, like a sheet of paper. If I keep stacking them on top of each other, what that's going to do is add the third dimension of height, which you can imagine this is all going to be part of the formula for the volume of a prism now. It's going to be the area of the base, which we just call big B, times the height, BH. A cylinder is going to be literally exactly the same thing, except we can get into more detail, because we know the area of the base is a circle. So I can get more specific than just BH. I can say pi r squared h. A pyramid, the thing that makes a pyramid a little bit different than a prism, is that instead of having two bases, it's almost like the top base shrinks into a point. So a pyramid is defined as being something with one base, that is some kind of polygon, being opposite a point that meets somewhere up top. So we would expect it, because it's so similar to a prism, except with one base instead of two, to have a volume formula very similar to that of a prism. And it does. For whatever reason. One I could explain with calculus, but don't worry about that. The volume of a pyramid is 1/3 that of its prism counterpart. So instead of base times height, it's 1/3 base times height. The same logic applies to a cone, which is comparable to a cylinder, in the same regard that a pyramid is comparable to a prism. And the volume formula works the same way. 1/3 pi r squared h. It's going to be 1/3 of the volume of its cone counterpart. A sphere is the one that's really out there, for whatever reason. This one, I'll just tell you. Again, I could prove it with calc and stuff, but you wouldn't, no offense, you wouldn't understand. You're not there yet. 4/3 pi r cubed is the volume for a sphere. Keep these in the back of your mind as we proceed forward. I'm going to just explain one useful theorem first that lets us solve pretty much anything we could possibly need to solve in future pages, and then we'll do some practice problems. So Cavalieri was some guy who noted that if I were to have two solids that have the same height and same cross sections as each other, then their volumes are going to be the same. So a good way to think of this is, imagine I have a stack of books, or like a stack of paper or something. If I were to shove the top of that and make the whole thing kind of slanted, like here's my stack of books or whatever, I slant it so that it looks like this, the volume is still the same. It's just that the areas, or each layer of it, is kind of displaced into a different location. We wouldn't expect that to change the volume. And Cavalieri noticed this, and he said that the volumes have to be the same. What this does for us is it allows us to find the volumes of weird things, like number 2 here, which is called an oblique prism. So this principle is useful for finding volumes of oblique solids, because we could say it has the same volume as 1 and 2 have the same volume. And as long as we could, in the way that we'd find 1, we'd find the area of the base times the height, we could do the same thing with number 2. And the thing that makes it oblique is that the base isn't perpendicular to the height in the way that it is to 1. So no matter what, if we have a prism, even if it's an oblique one or an ugly one, we're still looking for base times height. So I'm going to start with some problems. I would recommend pausing it, because I'm going to write the answers in advance before I begin discussing them. So if you want to try it on your own, pause it. Number 1's shape is a triangular prism. We know this because we can tell there's two bases that are both triangular, and they're opposite and congruent, yada yada. So this being a triangular prism means we need to find the area of the base, we need to find the height. The base being a triangle, and a right triangle, means we could see its base and height, its little b and h, pretty easily. It's 7 and 10. So that allows us to find an area of the base of 35 inches squared. The volume is then going to be that times the height of 5. So 35 times 5 is 175 inches cubed. Notice that our units are cubic inches in this case. Number 2 is a cone. It's a weird-looking cone, but Cavaliere's principle says doesn't matter how weird it is, we still have the radius, we still have the height, that's all we need. So 1/3 pi r squared h grants us, there's no way to do this without rounding, comes out to like 22.808 centimeters cubed. I should write that in. Centimeters cubed. Number 3 is a little bit more complicated than the other ones because we actually have to dig back into our geometry repertoire and either do some trig stuff or some special right triangle stuff. This triangle that I've drawn in purple is a 30, 60, 90, so I could use those properties to get that the height of this thing is 9√3. Be careful because in the diagram, the 12 meters isn't the radius, it's the diameter, which means that the radius is 6. If I plug all these things into the volume formula for a cylinder, pi r squared h, I get that it comes out to something like 1,300, oh my gosh, 1,763 point whatever meters cubed. Oh, that was a disaster. These problems on the next page, 4, 5, and 6. These are more interesting. These are called composite figures because they deal with not just one solid, but some combination of solids that are either being added or subtracted from each other in the case of number 6. If you've just been passively watching up until this point, please pause it and try these because, again, I'm going to pre-record the work before I actually begin talking and discussing it. 4 is a cube and not an entire cylinder, but half of one, which I think the proper term for that is a semi-cylinder. So what I did is I broke it up into those 2 different pieces. I found the volumes of each of them individually, and then I added them together at the end. So for the cube, we can see that the volume of the cube, which I found which I calculated right here, since the cube is 4 by 4 by 4, length, width, and height of 4, it's just 4 cubed. I could look at that as a prism, and the area of the base is 16 times the height is 4, which is still 64. Whatever. The only trick with this the only 2 tricks, I suppose, with the semi-cylinder is to acknowledge that, A, we need to take half the formula of a regular cylinder, so we take that and cut it in half, thus the coefficient of 1/2, and also finding the radius, because that's not explicitly spelled out to us, but still, if we recognize that this shares the base of the cube, and one of the sides is 4, that side of 4 is a diameter of the cylinder, so that tells us that a radius must be 2. If I plug in everything accordingly, I get 8 pi. I'm saving all my rounding until the end. When I add the 64 and the 8 pi, I get that this whole shape has a volume of 89.133 inches cubed. Number 5 here is actually not as bad as it looks. It can be broken up into a cylinder and... oh, geez, hang on. It can be broken up into a cylinder and a hemisphere. That's what half of a sphere is called. So if I look at the cylinder, this one's very straightforward. We have the radius of 5.8. We have a height of 14. Height isn't always vertical, remember. In this case, it's just the distance from base to base. So if we multiply those together, the pi r squared h, we get like 1,400. If I do the same with the hemisphere, that's half of the 4/3 pi r cubed. So what I did is I just did 1/2 times 4/3 to give me 2/3. And then multiply that by pi r cubed, which ends up getting me something like 408. I put these 2 values together, I added them to get the total cumulative volume of like 1,888. This last one's kind of a doozy. Notice, though, that instead of being 2 shapes put together, it's one shape being pretty much subtracted or removed from another, which would equate to the subtraction of their volumes. So the first shape, the bigger shape, the entire thing, is a cube. So we could find the area of that cube, no problem. It ends up being 1,000 because it's 10 by 10 by 10 cube. The piece being removed, and thus the volume to subtract, is that of a pyramid. A pyramid with a rectangular base, so I guess a rectangular pyramid, where it's a little bit not obvious how to find the area of that base, how to find big B. What I did, though, in the stars to designate, I'm using the fact that these congruence marks are there, to show that each side is pretty much going to be the hypotenuse of an isosceles right triangle. Isosceles right triangle things follow the, they are 45, 45, 90s. So I could use that property to say each hypotenuse, and thus each side of this pyramid's base is going to be 5√2. Thus, the base is, or big B, the base's area is 5 root 2 quantity squared, which is 50. So the volume of the pyramid, I'm now here, 1/3 BH is well, something like 166. 166 and 2/3. I'm keeping it in terms of decimals to stay consistent. So then, I'm not adding these like in the previous problems because this is not the two shapes combined. This is one subtracted from the other. So 1,000 minus 166-ish is 833 and a third.